Welcome to this preparatory lecture on the common data types you will encounter when conducting a freshwater health analysis. My name is Kashif Shad, and I am the Director of Hydroinformatics at Conservation International. In the topic that we will cover as part of this open online course, we will refer to and use a number of data types covering different aspects of freshwater health. This lecture will introduce you to key definitions and frameworks when talking about data that will assist you in following and applying the concepts introduced throughout this course. The lecture is divided into 3 parts. In the first part, we will consider data in a more conceptual manner. This should equip you with a framework to help think about data and its organization. The second part will consider topic linked to variation over space and time, and will include a brief introduction to GIS. And finally, the third part will focus on data as you may encounter in executing a freshwater health assessment. Moving then to the first part, let's begin with the definition of data. Data is defined according to the Cambridge Dictionary as information, especially facts or numbers, collected to be examined and considered and used to help with decision making. When performing a freshwater health assessment, we aim to describe a situation or phenomena that we are observing in precise terms. Therefore, we gravitate towards collecting quantitative data about it. Quantitative data is data in the form of counts or numbers where each data set has a unique numerical value associated with it. Simple examples of this will be height of water at a particular point, the number of endangered species in a lake, etc. The other category of data is qualitative data, where one would describe the situation or phenomena by way of facts or observation. In an assessment framework, this may not be very helpful, and we will try to convert qualitative data to quantitative data to assist in making comparisons. If you have ever visited a doctor who has asked you to rank your pain on a score of 1 to 10, that is an example of trying to convert qualitative data, your perceived pain, into quantitative data. That is a number between 1 to 10. So the doctor can assess how bad the situation is and what next steps are necessary. Data in quantitative terms alone may not be sufficient to make a direct assessment, and a final step may be required to combine different quantitative data sets and compare them against historical thresholds to understand what the data is telling us. This is the step of calculating indicators or metrics describing the state or trend. Decrease in complexity allows for ease of communication. At numerous points in this course, we will consider the methods and assumptions behind converting quantitative data to indicators. For now, let's take a step back and go towards the domain of deriving quantitative data and take an example to explore it further. Imagine you have organized a party and baked a cake especially for this occasion. You may want to describe this data in quantitative terms. The first piece of data you can collect is very simple and probably based on the physical properties of the cake, such as its size and weight. With a little bit of effort in accounting for all the ingredients you have used in the cake, you can likely make a good estimation of the calories you will be serving. So far, it's all fairly straightforward. But next, an actual question of interest for you may be, how good is this cake? Is it tasty? As you may have immediately recognized, this is a qualitative question. And to measure it in a quantitative way, you need to arrive at a method that suits your needs. There are 3 popular approaches to this type of problem. The first is to identify and use proxy observations. You may, for example, survey what remains of the food at the end of the party. If all the cake is gone, wiped clean, you may be justified in assuming a superb effort, 5 out of 5. If, however, most plates have huge chunks of cake left over, it is fair to assume a failure. The second approach is to get an expert's opinion. Maybe some of your friends are expert bakers, and getting their opinion will be a good way to determine how well you did. Making sure the opinions given are not biased because of your friendship is something you will have to account for. The final approach will be to survey the gathering itself. Maybe you could ask one of your friends to go and discreetly survey the guests on their reactions to the cake, deriving then an aggregate for your cake's taste score. Measurements of the physical aspect of the cake to its perceptual or social aspects is in some ways the two ends of data required for an assessment. We tend to refer to this as biophysical data and social data about a system. A category that sometimes combines these two ends is supply and demand. The supply in this case will be limited by the size of the cake. The demand, however, depends on the number of friends joining the party, but also how delicious was your cake. Replacing the cake with a much more complex and dynamic system, our freshwater ecosystems, we immediately become aware that several biophysical components will need to be measured. Different types of demands are acting on the freshwater ecosystems, and its management will involve stakeholders from diverse social contexts. In this course, each topic and each pillar of FHI will roughly match each of these categories. These are ecosystem vitality, which refers to the long-term maintenance of ecosystem structure and processes that underpin the capacity of an ecosystem to provide water-based goods and services. Ecosystem services, which are the range of benefits produced for stakeholders, and governance and stakeholders, which refers to the structures and processes by which people in societies make decisions and share power, creating the conditions for audit rule and collective action or institutions of social coordination. Our cake example dealt with a single object, the cake, over one instance of time, the time of the party. However, in more complex systems, the number of objects that need data will be many and scattered over space, and they may change over time. In the second part of this lecture, we will briefly examine this aspect. The aspect of tracking over time is very common, and we do it all the time, even without realizing it. For example, over the period of the pandemic, we have tracked the number of cases rising and falling with anticipation. One aspect of freshwater ecosystems that closely impacts time series analysis is the many cyclic elements of climate and season that underlie the collected data. Seasonal cycles can be distinctly seen in data of flow rates, for example, but regional climate patterns such as El Nino, which can have a footprint over several years, are also something to account for. And so indicators that require time series data will at times indicate the period and frequency your data must ideally cover to have higher confidence in the values being calculated. Spatial location is the second consideration, and the one that has grown in significance over the last few decades due to advancement in technologies such as global positioning system, the proliferation of satellites making Earth observations, and increased storage as well as processing power of everyday devices. While questions like where should we place a water quality gauge so that the data we get is representative has always been important, now we can gather and analyze data at spatial resolutions, details of coverage, and accuracies that were just not practical before. Any geospatial data you encounter in this course will be mainly of two types. The first type, raster datasets, are built from pixels or grid cells, where each pixel has a numerical value or a set of values denoting the attributes it measures. The dimensions of a single grid cell defines the real-world resolution of the dataset. Another way to record geospatial data is as vector data built from vertices and paths. This could include points coded as coordinates, polylines defining how those points connect, and polygons to complete a path. Raster and vector datasets both have their respective strengths and weaknesses when denoting spatial location of real-world objects or attributes. And based on this, we tend to prefer one type or the other for specific usage. In the context of freshwater assessments, some common examples of each type you see here on the screen. Remote sensing for digital elevation for satellite imagery, and vector datasets for location of rain gauges, networks of roads, rivers, and administrative boundaries. In most cases, we will be creating and manipulating or analyzing these geospatial datasets using a Geographic Information System, or GIS for short. The FHI desktop toolbox has built-in basic GIS functionality to display the basin shape and river network using an ArcGIS extension. QGIS is one of the most popular open source GIS software applications, and it can be used to visualize geospatial data sets used in this course. A detailed exploration of GIS is beyond our scope, but several resources are available online for those interested to learn more about it. One aspect to keep in mind is a spatial projection and coordinate reference system. Briefly, a coordinate reference system, or CRS, refers to the way in which spatial data that represents the Earth's surface, which is round and three-dimensional, is flattened so you can draw them on a two-dimensional surface. For example, imagine you have wrapped a huge sheet of paper around Earth and lit a powerful lamp at its center. If you now capture the shadow of the continents that fall on the scroll of paper and then unroll it, we get the 2D representation of Earth. There are, in fact, multiple approaches to flattening the data that are specifically designed to optimize the accuracy of the data in terms of length and area. As our Earth is large and not a perfect sphere, different methods work better for different purposes. Most nations have a national coordinate system that measures distances in meters and kilometers. Most global systems measures distances in degrees and arc minutes. Consequently, each uses a different mathematical approach to derive a coordinate system grid. In most cases, the geospatial layer will come with its own projection information so that the GIS software will know where to correctly plot the data in relation to your existing map. However, in some cases, it may not be so, or your analysis may require that the data is in the same coordinate reference system. Therefore, it is important to understand the coordinate system that your data uses, particularly if you are working with different data stored in different coordinate systems. With the conceptual framework for data in place and some considerations for documenting variation covered, in the third part of this lecture, let us consider the different types and sources of data needed for a freshwater health assessment. We discussed earlier 3 different ways that social data can be gathered using our cake analogy. The same ideas also apply for the governance and stakeholder data linked to measuring topics such as adaptive management of water resources to involvement of stakeholders in decision making. As a first option, we could use existing data and proxies. A good example of this is water consumption in agricultural production, where in many cases the demand for water can be estimated from the type of crop being planted and based on climatic factors, estimating the amount of water that crop will need to give the desired product and multiplying that with the area under cultivation. Expert opinion is useful when some specific or specialized information is needed, and at this point in time, perhaps enough vetted information about it is either not available or its interpretation is in doubt. Finally, surveying the body of stakeholders in the basin may be the most representative way to gauge demand of certain freshwater services and the effectiveness of water governance, etc. The variables that can be monitored under the biophysical category, especially ecosystem vitality of FHI, can be roughly classed into three approaches as well. The first are in situ or on-site point measurements. This is considered largely the gold standard of data as it is real for the point being measured, such as the water quality measured at a point in a lake through instrumentation, or monitoring biological quality elements, which consist of abundance and diversity measures of fish, fauna, phytoplanktons, benthic invertebrates, etc. However, it is labor intensive by nature, involving installation, maintenance, and retrieval from remote locations. In some cases, citizen science networks have been effective to collect scientific data for large areas. Depending then on the collection system, quality control issues may arise. Since data is only measured at one point, questions around if it truly represents the whole basin needs to be considered. Data extracted from satellite-based remote sensing missions is a second and growing source of data. While some of these data products may be too coarse yet to directly apply to our basin, their coverage and resolution continues to improve decade after decade. Use of precipitation data gathered by numerous satellites under the GPM, or the Global Precipitation Measurement Mission, for example, has become a valuable source for rainfall estimates across the world. Remotely sensed data is a good complement for in situ data with the advantage of greater spatial coverage. However, resolution and sensing limitations may impede usage. Finally, the third option is use of numerical models. These models ingest both in situ and remotely sensed data to provide continuous coverage of data for a region or a time period. As with every numerical model, the quality of the inputs and the understanding of the underlying phenomena dictates the quality of the outputs. Two common models you may come across when looking at studies done in your basin for freshwater management would be an example of a local hydrological model such as SWOT and a macro-scale hydrological model applied at global scales known as WIC. Numerical models, if applied correctly, are a valuable tool for freshwater management. The data requirements can vary widely depending on how complex the model is, as well as the scale it covers or the resolution of its outputs. Going back to our original motivation, we collect quantitative data to be able to describe the state and trend of the freshwater system and apply this knowledge for decision making. While the best data in most cases will be locally vetted, that sometimes isn't an option. In that case, it is better to have some information to base our actions on rather than no knowledge about the state of the system. In FHI assessments, we try to address this problem by identifying multiple tiers of data, as seen here with the example of surface water quantity, which goes from local to global and measured to modeled options. To deal with the uncertainty introduced by multiple sources of data, we encourage practitioners to do sensitivity tests with their calculations and indicate the level of confidence they have in the results obtained based on the data used. This can be a challenge, but we must remember that if those who know the data and calculation process best do not indicate the confidence they have in the numbers they are producing, someone else who likely knows much less about what is happening will make that assessment. So as we prepare to enter this course and get our feet into the basins we want to help protect the freshwater health for, I leave you with these points that may help you weigh the different choices in front of you to monitor, measure, and quantify different aspects of freshwater health. The first question you have to consider is what do you want to measure and at what detail? Secondly, how can you allow multiple grades of same data to coexist? And thirdly, how will you track the uncertainty across these multiple data sets? Please now proceed to the short video below on FHI resources to help identify the data processing tools and scripts we will use in this online course.